So this morning we already have heard talks about dark energy, about whether the neutrino is its own antiparticle, possibility to try and measure dark energy or measure extra dimensions in the laboratory. Those are all exciting things that are still unresolved. So this report was called Connecting Quarks to the Cosmos, and presenting 11 questions for the 21st century. So if we take a look, you've seen some of those. We talked about it. So what is dark energy? How did the universe begin? And so on. But the one I'm going to talk about is how were the elements from iron to uranium made? This is a problem that is embedded in astrophysics, astronomy, and nuclear physics. It turns out that we actually know the nuclear physics. We know how the nuclear physics works. What we don't know are the kinds of conditions in which the nuclear physics can operate. This was a takeaway from the video. The reason I wanted to show the world map with all the flags is that this question of how were the elements from iron to uranium made was a very strong motivation for the building of a lot of these facilities across the world. So it may not have been the only motivation, but it certainly was a strong motivation for Triumph, for FRIB at Michigan State, for Spiral at Ganil, CERN, GSI Fair, China, and Korea. And so it's an important enough question to have spurred all of this construction, at least in nuclear physics, for different facilities. So what is the problem? How are all the elements made? If we take a look at the chemical evolution history of the universe, we can understand it in very simple ways. So, well, we don't know. We think the Big Bang made some primordial elements. And from those primordial elements got processed in stars up to about iron or so, up to about iron 56 and a little bit higher. But really what we see today are elements, this is a mass fraction abundance number as a function of the mass. So what we see today in the solar system is this. We know that the oldest stars have abundances of masses up to about mass 60. And we believe that the Big Bang made some of these primordial elements. What's the physics here? What are the issues? This figure probably all of you saw in introductory physics course. The first time you had modern physics, you saw that the binding energy per nucleon as a function of mass number looks like this. The peak is about iron 56. So it makes complete sense that stars are where you make all the elements up to about iron or so. It's energetically profitable to do that and becomes less so after that. We also know enough nuclear physics that if we want to make heavier nuclei, so if we want to make what we observe today, we know that we can't do it with those charged particle reactions. We know that we can do those with incorporating neutrons, neutron reactions, beta decays, and so on. So we basically invented two processes here. It's called the slow neutron capture process and the rapid neutron capture process as a way to say, well, that if we want to make heavier elements, that's how we could do it. Particularly the rapid neutron capture process. It's rapid in the sense that you make successive neutron captures before you beta decay. So you get further away and you can make much heavier nuclei and sort of fill in things that the stars don't. So what are the issues? From the nuclear physics side, we know that you can do neutron captures and reverse processes. And in fact, a slow neutron capture process goes along the line of stability and it's fairly well understood. But it's the rapid neutron capture process that's a challenge. It's a challenge for nuclear physics. It's a challenge for astrophysics. It's not a challenge for astronomy because the observers have very robust signatures and in many different cases. So what's the nuclear physics? What are the input parameters that go in? So if we're going to neutron capture and beta decay, we care about the nuclear masses or mass differences. We care about the beta decay rates. We care about neutron capture cross sections. And we care about beta delayed neutron emission rates. Do we know how all of these work? Yes. Do we know how they behave in different competitive situations? In principle, we do, but what we don't know is what happens. So beta decay rates vary and neutron capture rates vary depending on if we're a closed shell or away from a closed shell, whether the nucleus is deformed or spherical. So all of those have a huge impact. So what are the unknowns? The unknowns from nuclear physics is, but we don't know the properties of these nuclei. The talks we heard from Katrin Wimmer, and Elizabeth Padilla yesterday, where they were talking about neutron-rich nuclei, there were surprises every time. So we don't know where you have subshells, where you have shell closures, which ones hold and which ones don't. So those are the kinds of things that are in competition, and we really don't know what happens when you go to very neutron-rich nuclei in the heavier cases as well. So those were examples of what happens in the lighter cases, but we also don't know what happens there. What about astronomy? There have been many observations, and what is shown here is basically these are all normalized, and it shows the abundance pattern for different stars. This is compiled by John Cohen and company. Everywhere you look, the signature is extremely robust. So this indicates that whatever process was responsible for making the heavier things had to be fairly robust, had to be the same, somehow. What's the problem in the astrophysics side? Well, the astrophysicists don't have the right conditions to make the kinds of nuclear physics that is required to make the very heavy elements. We know how neutron capture works, we know how beta decay works, but what we don't know is what the nuclear structure is further away from stability, and the astrophysicists can't tell us which scenario is responsible for the production of these elements. An idea which was fairly popular was the core collapse supernovae winds. The time scale for these things just don't work out right in terms of the nucleosynthesis. There's the two neutron star merger sort of scenarios. The time scale is perfect here, but they don't make enough neutrons. There aren't, to date, as many neutron star mergers in the universe for us to have created the heavy elements. So the question is, how do you do this? So how were the elements from iron to uranium created? So let's delve into the nuclear physics side. I mentioned that masses are important, beta decay rates, neutron capture rates, and so on. What is shown here is just a plain chart of nuclides. Black boxes are stable nuclei, and what's shown in this orange set of boxes is a possible our process path, a possible path that rapid neutron capture takes. But what is highlighted in the middle here on this plot, this is solar abundances as a function of mass number. The black points are the observed solar abundances. And the two different colored lines, in this case it looks like orange and purple, are two different mass models. two different mass models in which one of them, the major shells are quenched versus the other one. So it says these are both the ETF-SIQ type of mass models, which are very similar basis except for the quenching of the major shells here. So if you can put in mass models which have different major shells, magic shell numbers, you're going to get very different abundances for the solar abundances. So in terms of the challenges, the problem just being in between fields, and usually nuclear physicists make advances and astronomers make advances, people don't talk to each other, and astrophysics has its issues as well. So the question of how does deformation set in? A very old problem. I think the first time I thought about it, I read papers by Stewart, sitting here, but still a major challenge. I'm an experimentalist, so in order to try and solve some of these problems, we were thinking, okay, we'll set out, we'll make some measurements. Which ones do we measure? So which nuclei do we measure? I show this approach here. One was to try and go and make measurements near closed shells. This is a publication from 2005. It's fairly old already, but it was the first measurement of nickel-78. Nickel-78, doubly closed shell nucleus. Measuring the half-life gave us some information about the property of this nucleus, which is at a closed shell. And then we thought, okay, what is the impact of this measurement on the art process? Does it change anything? Here is a calculation of the solar abundances in dark here. The green line that's shown here is a calculation done with Peter Moller's mass model, VFRDM. It takes the theoretical value for nickel-78 half-life. I know we did one where we just put in the measured value for nickel-78.